Hello everyone, we are Team Unknown and I'm Sunya. Today we will be presenting our final project for the DA 422 course. Our project is titled Extending Learning Distances from Data to Large-Scale Image Datasets. In simple terms, we explored how to move from raw pixel space to meaningful geodesic distances on the data manifold using normalizing flows. I'll begin by giving a short overview of the problem we are addressing, and then the rest of the team will walk you through the architecture, the algorithm, and our experimental results. Let me start with an overview of the problem we are addressing. The problem is that standard Euclidean distance does not work well in high-dimensional image spaces. The usual distance measure, which is the L2 norm, completely ignores the semantic structure of the data. So a straight line between two images often passes through regions of low density, or what we can think of as an empty space. This path does not follow the actual data manifold. To address this, we look at Fermat distances. Here the idea is that the cost of moving through a region should depend on its density. So paths should be cheaper in higher densities where real data is concentrated and more expensive in low density regions. But this brings us to the main challenge. Most existing graph-based methods fail to compute these distances reliably in high dimensions because of the curse of dimensionality. They either don't converge or require unrealistic amounts of data. This sets up the motivation for why we extend the original method and why we later introduce normalizing flows to estimate density more accurately. Now that we have looked at the problem, let's talk about how we can extend the original work. The original paper was validated only on MNIST, which is a very small and simple data set. The results good look there, but MNIST does not represent the complexity of real-world images. So our main contribution is scaling this approach to much more challenging datasets, specifically CIFAR 100 and Tiny ImageNet. Both are high resolution, more diverse, and much more complex than MNIST, which makes density-based geometry significantly harder. To make this possible, our method is built around three components. First, latent space projection. Instead of working in raw pixel space, which is extremely high dimensional and sparse, we use ResNet-based autoencoders to compress images into a meaningful latent representation. Secondly, density estimation. We apply normalizing flows on these latent embeddings to learn an exact tractable density function. This gives us the density information needed for Fermat distances. And third, path refinement. Using score matching, we smooth the initial paths to produce clean geodesics that follow the underlying data manifold. Together, these steps allow us to scale density-based geodesic learning from MNIST to far more complex datasets. Before we move into the architectural details, I want to quickly introduce a few basic concepts that our method relies on. First, let's talk about density, P of x. Density is a measure of how packed the data is in a particular region. In the context of images, real and meaningful samples lie in high density regions, whereas random noise or invalid images lie in low density regions. Understanding this distinction is important because our distance metric depends directly on density. Next is Fermat distance, which is the core idea behind the geometry we are trying to learn. A useful way to think about it is the analogy of light traveling through glass. Light bends towards regions where it can travel faster, minimizing time. In the same way, Fermat distance encourages paths to bend toward high density regions where real data lives. Formally, this is defined using a metric tensor where the cost of moving between 2 points is scaled by 1 upon density square multiplied by a parameter beta. The parameter beta controls how strongly the density influences the path. A higher beta means the path will stick even more closely to high density regions. Finally, to compute this distance, we need an exact estimate of P of x, which brings us to the normalizing flows. A flow model transforms a complex distribution like images in latent space into a simple Gaussian where the density is known. By tracking how this information changes volume, we can compute an exact tractable log density for any point. This gives us the precise density information needed to define format distances. With these basics in place, the next speaker will walk you through how we apply these ideas in our architecture.
Thanks, Sonia. Hello everyone, I'm Syama and I'll walk you through the internal workings. While the theory of format distance is elegant, implementing it on high dimensional data like Cipher 100 or Tiny ImageNet requires rigorous engineering pipeline. If you look at this slide, you can see an overview of our system. It is not a single model, but a chain of three distinct neural networks working in sequence. We don't process input image directly. Instead, we pass it through autoencoder to get us a compressed latent vector. Once we have that vector, the pipeline splits. One branch we train normalizing flow to learn the density. On other branch we train score model to learn the gradients. Finally, these two outputs converge to build our graph, which initializes the path for our final refinement step. Now let's dive deep into dimensionality reduction. You might ask, why can't we just run math on pixels? The answer is because of dimensionality. Cipher 100 images have over 3K dimensions and Tiny ImageNet has over 12,000 dimensions. In large dataset, data becomes incredibly sparse. It's like finding needle in the universe of empty space. Traditional density estimation fails completely here because you would need exponential amount of data to fill that space. To solve this, we implemented deep convolutional autoencoders. We didn't just use standard flat networks, we used ResNet style residual blocks to capture complex spatial hierarchies. We trained these networks to compress the data into dense manifold. For Cipher 100, we compressed 32 times so that the image has latent vector dimension of 128, and for Tiny ImageNet, we compressed 64 times to get 256 dimension latent vector. Once we have these latent vectors, we move to density estimation. We need a function that outputs the exact probability Pz for any point in the latent space. This is harder than it sounds. Standard GANs or variational autoencoders do not give us exact likelihood, they only give us approximations. So we utilize normalizing flows, specifically using real NVP architecture. Normalizing flows are powerful because they are invertible. They work by learning a sequence of bijective transformations that map our complex messy data distribution into simple standard Gaussian distribution. Because the transformation is invertible, we can use the change of variables formula. By calculating the determinant of Jacobian matrix at each step, the flow gives us the mathematical precise density value for every point in our space. This gives us the elevation map of our manifold, telling us exactly where the high density clusters are and where empty voids lie. Finally, we have score estimation. While the normalizing flow gives us the map, the density, it doesn't effectively tell which direction is the uphill towards the data modes. This is where the score model comes in. The score is mathematically defined as gradient of log probability density with respect to the input data. We model this using separate multi-layer perceptron with soft plus activations. Now, training a model to predict gradients is tricky. We use technique called sliced score matching. Usually, calculating the gradients in high dimensions require computing Hessian matrix, which is computationally expensive. The sliced score matching uses a stochastic critic called Hutchison trace estimator. It projects the high dimensional data onto random vectors, allowing us to train the model to learn the shape of the manifold efficiently. So, to summarize, the autoencoder gives us the space, the flow gives us the map, and the score model gives us the compass. With these three models trained, we have everything we needed to start building the paths. I will now hand over to Vidhi to explain how we use these outputs to construct the graph.
Hello everyone, I'm Vidhi and I'll walk you through the next steps in the process. Once our normalizing flow and score network are meticulously trained, the heavy lifting of density estimation is complete. Now we are ready to build the geometry of the manifold. This is done in step 4, that is the graph construction. We begin by taking the clean compressed representations of our images or the latent vectors and constructing a k nearest neighbor graph or the KNN graph. We selected k is equal to 20 so that sufficient local connectivity is ensured, which is important in a high dimensional space where sparsity or the curse of dimensionality can easily lead to disconnected components. The standard approach would be to simply weight these edges with Euclidean distance. But as earlier mentioned, that distance cuts through empty space. Empty space is the low density voids that have no semantic meaning. Therefore, we use the density information from our normalizing flow to weight the edges according to Fermat's distance principle. If you recall the light traveling through glass analogy, light bends and slows down as it enters dense material. Here the opposite is true. We define our distance such that when the path segment between 2 points passes through a high density region, the edge cost is low. Conversely, if the path tries to cut through a low density region, the cost is high due to the parameter beta. We achieve this mathematically by discretizing the path segment and approximating the integral as shown in the equation. The distance is the sum of the physical lengths of the segments yi minus 1, but each is divided by the density p at its midpoint, raised to the power of beta. This is the function that determines whether a connection is semantically meaningful. The result of step 4 was a fully connected, high-quality, density-weighted graph. Now we move to step 5, that is path initialization. We now use a classic shortest path algorithm, specifically Dijkstra's algorithm or A star, on this graph. Dijkstra is designed to find the optimal sequence of nodes that minimize the total sum of edge weights. Since our edge weights are the Fermat's distances, the output, that is our initial path, which is phi init in the slide, is the sequence of points that follows the path of least density weighted resistance. This step is absolutely critical. If we simply started with a straight line Euclidean path between our 2 points, the subsequent gradient-based optimization would almost certainly fail. You may think why? Because the straight line would immediately fall into those low density voids that we wanted to avoid. The optimization, which is guided by the density gradient, would then have no strong force to pull it back onto the manifold, and it would get stuck in a local minimum. Dijkstra's algorithm solves this. It gives us a topologically correct starting sequence, ensuring that we begin in the high density neighborhood, which is the necessary prerequisite for our final smoothing step. Having found our initial path using the Dijkstra's algorithm, we arrive at the final crucial step, the geodesic refinement. The path that we initialized is still a sequence of discrete nodes, and it is jagged and rough. We must now transform this into a smooth continuous curve that satisfies the principles of differential geometry. This smooth curve is the true geodesic. We achieve this by using the score model. As we discussed earlier, the score function S of z estimates the gradient of the log density. Basically, this gradient is a force vector that tells us the direction of steepest density increase and points directly towards the nearest high density region. The core of this process is satisfying the geodesic equation. This equation defines the mathematical condition for a path of minimal density weighted length. Since this differential equation is complex to solve directly, we solve it iteratively using a relaxation update rule. If you look at the update rule shown on the slide, the term average of phi I plus or minus 1 smoothly pulls the point towards the center of mass of its immediate neighbors, which is a standard method for path smoothing. The second complex term involves S of phi, that is the score, and Vi, that is the velocity. This is the geodesic force correction. It calculates the precise force needed to nudge the internal points of this path towards the mode of the distribution and counteracts the curvature caused by the low density noise, ensuring that the path adheres to the manifold structure. The process of iteratively applying the relaxation update rule smooths the path over many steps, and the result is visualized here. The red dashed line represents the initial Dijkstra path, the rough route found on the discrete graph. The blue solid line is our refined geodesic, which is a smooth curve that has been pulled and relaxed to accurately follow the high-density manifold of the MNIST data. This smooth density-aware curve is the distance metric that we use to calculate superior performance in local retrieval tasks. Next, we shall show and explain the experimental results.
In this slide, we compared our format distance, the smart density aware path, against the standard Euclidean distance, which is the straight line on large image sets. We found two very important things. First, contrary to the theory, the Euclidean distance showed a higher NMI on our high dimensional datasets, Cypher 100 and Tiny ImageNet, which is, as you can see, 0.7 versus 0.57. This suggests that for global clustering, the noise in the high dimensional latent space overwhelmed the density signal, which means Euclidean handles global embedding noise better. While in the retrieval or precision at 5, we saw a clear win for the format path, especially on Tiny ImageNet, with a positive 16.7% improvement in precision at 5. This proves that the format path is much better at finding the true or immediate semantic neighbor for an image. So, format wins on local precision. Moving on to the next slide, the normalizing flow we trained has a bonus function. It's an excellent out of distribution or OOD detector. The flow models the density of real data. If we feed it random noise, the likelihood should drop. We saw large successful gaps in density scores. For our cipher model, the score of a real image was very high, that is minus 125, but when we fed it noise for the OOD image, the score dropped dramatically, that is to positive 37. This confirms that the flow successfully learned the boundary of what a real image manifold looks like, giving us a robust tool for anomaly detection. In this slide, we discuss about efficiency. The core challenge of this project was making the method fast enough to be practical. So our two-stage pipeline solved this. We first moved all the tough math from the high pixel space, which had over 3000 dimensions, to a much smaller latent space, which only had 128 or 256 dimensions. This cut our training time from what would have taken days in pixel space down to minutes in the latent space. The final inference speed for the flow and score models is also very fast, which is around 5 milliseconds per batch. This confirms the entire pipeline is fast and scalable. Second, the clustering and retrieval results highlight a critical strength of the format distance. On this simple MNS dataset, format distance showed a huge win in global clustering. NMI was positive 51.1% better than Euclidean. On the complex Tiny ImageNet dataset, format excelled locally. Precision at 5 was positive 16.7% better than Euclidean. So the main takeaway is clear. Format distance excels at local retrieval. It's the perfect tool for navigating the immediate semantic neighborhood because it uses density to find the true curved path on the data manifold. Let's now summarize the scalability and feasibility of our entire pipeline. First, we successfully extended density-based metric learning from the simple data MNIST to a complex image manifolds. which had Ziffer 100 and Tiny ImageNet. We also confirmed the method is fast and feasible by moving the geometric processing to the compact latent space, which had 128 dimensions. This resulted in the training time dropping from days to minutes with a negligible inference overhead of around 5 milliseconds per batch. In addition, this method has a dual utility. The entire pipeline functions as a highly effective out of distribution detector. What was the result? The normalizing flow consistently assigned much lower likelihoods to noise or OOD data compared to real images. This proves the flow learned the true support of the data manifold, allowing it to flag anything that falls outside of it. Let us now summarize our key findings. First, we learned about the trade-offs of using a density-based metric in a high dimensional space. The format distance proved it is superior for finding immediate neighbors. It outperformed Euclidean in local retrieval, meaning it finds the true semantic neighbor much better. This was highlighted by the positive 16.7% precision win on Tiny ImageNet. However, we saw that Euclidean distance is better for global clustering. This happens because the format method is so sensitive that it amplifies artifacts or noise present in the latent embedding space. Even with the imperfect global separation, the path following mechanism itself works perfectly. The geodesics effectively capture immediate semantic neighbors. This now leads us to the limitation and the next step for this project. Our method is currently highly sensitive to the quality of the initial image embeddings produced by the simple autoencoder. The solution is to integrate modern self-supervised encoders like SimCLR or CLIP. These tools are designed to create much cleaner, more organized manifolds, and we expect they will resolve our global clustering issues. In conclusion, we successfully validated the robust technical scalability of the format distance, extending its application from the 2D toy data up to 256-dimensional complex image manifolds. This feasibility was achieved via our latent space pipeline, which cut computational overhead from days to minutes. We proved the system's dual utility, confirming its effectiveness as a highly robust out of distribution detector. While global clustering in high dimensional data remains challenging due to latent space noise, the method confirms its strength in local manifold aware retrieval. Thank you.